A very warm welcome, everyone. Today, I, Aditya, and Shamshir, the authors, will be presenting you the research paper titled Deep Learning Approach for Detection of COVID-19 using chest X-ray images using convolutional neural networks. Research was done over a span of 6 months in association with Bill Institute of Technology and Science, Dubai campus. The presentation is divided into 7 parts. We will be starting with the background of the problem, our objective, the dataset we worked on, our hypothesis and methodology. Finally, we will cover the experimental results and the conclusion of this research. COVID-19 is an ongoing pandemic caused by severe acute respiratory syndrome. The virus was first identified in mid-December 2019 in Hubei province of Wuhan, China, and by now has spread throughout the planet. With more than 75.5 million confirmed cases and more than 1.87 million deaths. Global population has witnessed a very high mortality rate in some states. The death toll around the world is increasing day by day. With the limited number of COVID-19 test kits available in medical facilities, it is important to develop and implement an automatic detection system as an alternative diagnosis option for COVID-19 detection that can be used on a commercial level. Chest X-ray is the first imaging technique that plays an important role in diagnosis of COVID-19 disease. Computer vision and deep learning techniques can help in determining COVID-19 virus with help of chest X-ray images. Due to the high availability of large-scale annotated images, great success has been achieved using convolutional neural network for image analysis and classification. The datasets used to train the proposed model is a combination of two open-source datasets called COVID-19 image data collection and COVIDNet. The COVID-19 image data collection was initially built by collecting medical images from websites and research publications, such as Italian Society of Medical and Interventional Radiology. The combined dataset after filtration consists of 9,438 chest X-ray images, which are categorized into two labels, and those are COVID and normal. During the data preprocessing step, all the chest X-ray images from the images dataset were cropped prior to the training of the model to mitigate commonly found embedded textual information in the images. Further, in order to avoid the overfitting and increase the size of the dataset, the data augmentation was leveraged with the following properties as shown. The following are the attributes of the dataset used to construct the dataset. These are patient ID, symptoms, gender, age, type of pneumonia, survival from past disease, post anterior for X-rays and coronal for CT scans, images of CT and X-ray scans, date on which the image was acquired, location of the hospital, file name, digital object identifier, the URL of the website, license of the image, and finally the clinical notes. In this paper, we propose a deep convolutional neural network. Deep CNN uses multiple feature extraction at different stages that automatically learns the features represented in the image of the dataset, giving it an edge over the basic convolutional neural network when it comes to accuracy and efficiency. Also known as the base layer for CNN, the convolutional neural network layer is responsible for feature extraction and pattern recognition of input images. Images from the training dataset are passed through filter consisting of feature maps and kernels, which help the CNN to extract low-level and high-level features. The kernel present in the filter layer is a matrix of size 3 by 3 or 5 by 5, which is transformed with the input feature matrix. After the features are extracted in the convolutional layer, their approximate position relative to others is much more important as compared to the exact location. The pooling layer, also known as a downsampling layer, is then used to aggregate similar information in the neighborhood of the feature layer, and the outputs are dominant response within this layer. The fully connected layer is used at the end of the deep CNN network for classification and is the most important layer of CNN. The function of the fully connected layer is a global operation. The input is a features extracted from different stages of the network and is then compared and analyzed with the outputs of the preceding layers. The role of the activation function is to transform the weighted sum input of one node from a layer and use it for the activation of the node for the particular input. The activation function serves as a decision function, helping in the learning of feature patterns. Batch normalization is a layer that allows every layer of the network to do learning more independently. It is used to normalize the output of the previous layers, which help in addressing the issue related to the internal covariance shift within the feature matrix. The internal covariance shift is a change in the distribution of the hidden unit values. It slows down the convergence and requires careful initialization of parameters. Finally, the dropout is used to add regularization within a deep CNN network, which proves generalized by skipping some units of connection with a certain probability at random. This removal of random connections or units generates several thin network architectures, and out of these, one network with small weights is selected.
Moving on to the next layer, the flattened layer is used to convert the pool feature map into a one-dimensional array as an input to the next layer in the form of a single long feature vector. In the proposed model, the flattened layer has converted the output convolutional layer into a single one-dimensional array of size 128 units. The following is the architecture of the proposed deep convolutional neural network built using 5 max pooling layers, 5 convolutional layers, 3 dropout layers, and 5 batch normalizational layers. Moving on to the result part, it was observed that the model had an accuracy of 96.82% on the training set and an accuracy of 92.63% on validation set. The loss generated during the training and validation set are 0.0971 and 0.293 respectively. Accuracies generated by the model on both the sets, training set and validation set, are marked on the graph during the 12 epochs time period. Losses generation by the model on both the sets, training and validation, are marked on the following graph during 12 epochs time period. 10 criteria were used for the performances of the proposed deep convolutional model shown in the following table. These are sensitivity, specificity, precision, negative predictive values, false positive rate, false discovery rate, false negative rate, accuracy, F1 score, and Matthews correlation coefficient, where TP, FP, TN, and FN represent the number of true positive, false positive, true negative, and false negative respectively. The figure shows output generated by the proposed deep convolutional neural network. It shows the correctly predicted normal chest ray image and COVID positive chest ray X-ray image, respectively. The final accuracy and the loss generated by the proposed model is compared with 4 different models which are being used currently for commercial and research purposes. The 4 models are COVIDNet, ResNet 18, ResNet, and MobileNet version 2. COVIDNet is a neural network specifically proposed to identify COVID-19 pneumonia CXR images. ResNet 18 is used as a residual network. An identity mapping layer is combined with the basic deep neural network to increase the depth of the fully connected layers. ResNet is based on the residual neural network using split transform merge strategy to convert single core convolution into multi-core convolution. But the topology is same as ResNet 18. MobileNet version 2 is different from the residual network. In contrast to ResNet 18 and ResNet, which first uses convolutional kernel to compress and extract features and then expand. On analyzing the results from the table, MobileNet version 2 has a larger accuracy gap, while ResNet 18 has smaller accuracy gap. If considering the number of parameters at the same time, MobileNet and ResNet 18 have a higher performance. MobileNet has the fewest parameters and the lowest accuracy. ResNet 18 has the second fewest parameters and the highest accuracy, while COVID-19 has the highest parameters but less accuracy as compared to ResNet 18, ResNet, and the proposed model. In this work, we have proposed a deep convolutional neural network design specifically for the detection of COVID-19 cases by implementing computer vision and image analysis on chest X-ray images gathered from 5 open access dataset repositories. The dataset comprised of 9,472 X-ray images from more than 13,870 patients. We conducted experiments on COVID-19 identification and compared it with 4 models: COVIDNet, ResNet 18, ResNet, and MobileNet version 2. And comparison experiment between the accuracy and loss generated on the validation set by each model. The experimental results show that the proposed model has the best performance accuracy on the validation set. Further, we investigated the applied different model parameters in order to gain deeper insights on COVID chest X-ray features critical for classifying COVID and non-COVID patients, which can aid clinicians in improve screening as well as improve trust and transparency.